Flue-gas dew-point corrosion damage mechanisms is a part of uniform or localized loss of thickness. Description of flue-gas dew-point corrosion based on API 571, Number A, sulfur and chlorine species in fuel will form sulfur dioxide, sulfur trioxide and hydrogen chloride within the combustion products. Number B, at low enough temperatures, these gases and the water vapor in the flue gas will condense to form sulfurous acid, sulfuric acid and hydrochloric acid, which can lead to severe corrosion. Flue-gas dew-point corrosion is a type of corrosion that occurs in thermal power plants, industrial boilers, and other combustion systems where flue gases are produced. It happens when the flue gases cool below their dew point, leading to the condensation of water vapor and the formation of acidic compounds. This corrosion can severely affect equipment, reduce efficiency, and ultimately lead to costly repairs and maintenance. Here's a detailed description of flue-gas dew-point corrosion. Number 1 is causes of flue-gas dew-point corrosion. Number A, of causes of flue-gas dew-point corrosion is condensation of flue gases. Flue gases, primarily composed of nitrogen, N2, carbon dioxide, CO2, and water vapor, H2O, can cool during heat exchange processes or due to temperature drops in exhaust systems. When the gas temperature falls below the dew point, water vapor condenses. Number B, of causes of flue-gas dew-point corrosion is formation of acids. The condensation process leads to the formation of liquid acids, primarily sulfuric acid, H2SO4, from sulfur compounds, SO2 and SO3, in the flue gases and hydrochloric acid, HCl, from chlorine compounds. These acids can significantly alter the pH of the condensate and contribute to corrosion. Number 2 of detailed description of flue-gas dew-point corrosion is mechanisms of corrosion. Number A, of mechanisms of corrosion is acidic environment. The presence of acids in the condensed water significantly lowers the pH, making the environment highly corrosive to metals, especially carbon steels and low-alloy steels. Number B, of mechanisms of corrosion is corrosion types. The first of corrosion types is uniform corrosion, often happens over the entire exposed surface, leading to thinning of the material. The second of corrosion types is pitting corrosion, can occur in localized areas, causing small, deep cavities to form in the metal. The third of corrosion types is stress corrosion cracking, SCC. The combination of tensile stress and a corrosive environment can lead to cracking in susceptible materials. Number 3 of detailed description of flue-gas dew-point corrosion is consequences of dew-point corrosion. Number A, of consequences of dew-point corrosion is material degradation. Corrosion leads to the thinning of the metal and potential failure of components, affecting the structural integrity of equipment. Number B, of consequences of dew-point corrosion is reduced efficiency. Corrosion can impair the performance of heat exchangers, increasing operational costs due to decreased thermal efficiency. Number C, of consequences of dew-point corrosion is economic impacts. Frequent repairs and replacements are required to address the damage caused by corrosion, leading to higher maintenance costs and downtime. Number D, of consequences of dew-point corrosion is safety risks. In severe cases, corrosion can lead to leaks, catastrophic failures, or environmental hazards if containment systems fail. In conclusion, flue-gas dew-point corrosion is a significant concern in any system that generates flue gases, primarily due to the condensation of acidic components. Understanding its causes, manifestations, and mitigation strategies is essential for maintaining the integrity of equipment and optimizing operational efficiency in industrial processes. Regular inspections and proactive maintenance are key to managing this type of corrosion effectively. Flue-gas dew-point corrosion affected materials based on API 571, carbon steel, low-alloy steels and 300 series SS. Flue-gas dew-point corrosion primarily affects a range of materials, particularly metals, that are commonly used in the construction and operation of equipment dealing with flue gases. The specific materials vulnerable to this type of corrosion include: Number 1 is carbon steel. Carbon steel vulnerability. Carbon steels are commonly used in many industrial applications due to their strength and cost-effectiveness, but they are highly susceptible to acidic corrosion, particularly when exposed to acidic condensates from flue gases. Carbon-steel corrosion mechanisms, uniform corrosion, pitting, and localized corrosion types are typical. The presence of condensed sulfuric acid and hydrochloric acid exacerbates the corrosion process. Number 2 of the specific materials vulnerable to this type of corrosion include low-alloy steels. Low-alloy steels vulnerability. Low-alloy steels, which contain small amounts of alloying elements to improve their mechanical properties, may also suffer from corrosion in acidic environments created during flue gas condensation. Low-alloy steels corrosion mechanisms. Similar to carbon steels, these materials can experience localized corrosion and general material degradation. Number 3 of the specific materials vulnerable to this type of corrosion include stainless steels. Stainless steels types. Austenitic stainless steels, such 304 and 316 grades, are generally used in situations where corrosion resistance is needed. Stainless steels vulnerability. While stainless steels offer better resistance to corrosion compared to carbon steels, they can still be vulnerable to pitting corrosion and stress corrosion cracking, SCC, in the presence of chloride ions and acidic condensates at or below the dew point. Stainless steels consideration. Using higher alloyed stainless steels, such as duplex or super duplex stainless steels, can provide improved resistance. Number 4 of the specific materials vulnerable to this type of corrosion include copper alloys. Copper alloys vulnerability. Copper and its alloys can be affected by flue gas condensates, particularly in the presence of acidic environments. Copper alloys corrosion mechanisms. Pitting and stress corrosion cracking can occur in copper and brass under such conditions, primarily due to the presence of aggressive ions in condensates. Number 5 of the specific materials vulnerable to this type of corrosion include aluminum alloys. Aluminum alloys vulnerability. Aluminum is more resistant to corrosion due to its natural oxide layer, however, in the presence of acidic conditions from condensates, it can still corrode. Aluminum alloys corrosion mechanisms. General corrosion can occur, particularly when aluminum is subjected to acidic conditions for prolonged periods. Number 6 of the specific materials vulnerable to this type of corrosion is concrete and refractory materials. Concrete and refractory materials vulnerability. While not metals, concrete surfaces and refractory materials used in chimney liners, ducting, and boiler systems can be affected by acidic condensates. Corrosive conditions can lead to degradation of these materials. Concrete and refractory materials corrosion mechanisms. Acid attack can lead to deterioration, spalling, and loss of structural integrity over time. Number 7 of the specific materials vulnerable to this type of corrosion is coatings and linings. Coatings and linings vulnerability. Protective coatings applied to metal surfaces may degrade due to the acidic conditions created by flue gas condensates. Coatings and linings corrosion mechanisms. Coatings can blister, peel, or wear away, exposing the underlying material to corrosion. Number 8 of the specific materials vulnerable to this type of corrosion is gasket and seal materials. Gasket and seal materials vulnerability. Non-metallic materials used for gaskets and seals, such as rubber, plastics, and composites, may weaken or degrade in acidic environments, posing risks of leaks and failures. In conclusion, flue gas dew point corrosion can significantly impact a variety of materials used in industrial settings. The selection of appropriate materials, considering their corrosion resistance when exposed to acidic environments, along with the implementation of protective measures, is vital for maintaining equipment integrity and ensuring long-term operational reliability. Regular maintenance and monitoring are also essential to mitigate the effects of this type of corrosion. Flue gas dew point corrosion critical factors based on API 571, Number A, the concentration of contaminants, sulfur and chlorides, in the fuel and the operating temperature of flue gas metal surfaces determine the likelihood and severity of corrosion. Number B, since all fuels contain some amount of sulfur, sulfuric and sulfurous acid dew point corrosion can occur if the metal temperatures are below the dew point. Number C, the dew point of sulfuric acid depends on the concentration of sulfur trioxide in the flue gas, but is typically about 280 degrees Fahrenheit 138 degrees Celsius. Number D, similarly, the dew point of hydrochloric acid depends on the concentration of hydrogen chloride. It is typically about 130 degrees Fahrenheit, or 54 degrees Celsius. Flue-gas dew point corrosion is a multifactorial issue that can significantly impact industrial systems such as boilers, gas turbines, and combustion processes. Understanding the critical factors that contribute to this type of corrosion is essential for effective prevention and mitigation strategies. Here are the primary critical factors related to flue-gas dew point corrosion damage. Number 1 is temperature. Dew point temperature, the temperature at which flue gases cool down below the dew point, is crucial. If the flue gas temperature drops below the dew point, water vapor condenses, leading to the formation of corrosive condensates. Surface temperature, the temperature of the metal surfaces in contact with the flue gases, also plays a critical role. Maintaining these surfaces above the dew point temperature can minimize condensation. Number 2 is chemical composition of flue gases. Presence of sulfur compounds, the concentration of sulfur dioxide, SO2, in the flue gas, which can oxidize to sulfur trioxide, SO3, significantly influences the formation of sulfuric acid in the condensate. Chlorine and other corrosive elements, the presence of chlorine compounds can lead to hydrochloric acid formation, which further exacerbates corrosion. Additional compounds such as nitrogen oxides, NOx, may also contribute to corrosive phenomena. Number 3 is pH of condensate. Acidity, the pH level of the condensate formed from condensing flue gases, is a critical factor. Low pH values, high acidity, enhance the corrosive potential of the condensate, leading to faster material degradation. Number 4 is material properties. Corrosion resistance, the selection of materials is vital. Metals and alloys with higher intrinsic corrosion resistance, like some stainless steels, nickel alloys, will perform better than standard carbon steels in corrosive environments. Surface condition, the condition of the surfaces, such as presence of protective coatings, surface finishes, can influence the rate of corrosion. Number 5 is humidity and moisture content. Condensate formation, higher humidity levels in the combustion air can increase the amount of water vapor in the flue gases, raising the potential for condensation and corrosion. Moisture content directly affects how much acidic condensate is formed. Number 7 is operational factors. Load cycles, fluctuations in operational load can lead to varying temperatures in flue gases, thereby impacting the cooling rates and potential for dew point corrosion. Heat recovery systems, the efficiency and design of heat recovery systems, such as economizers, can affect temperature drop rates and the potential for condensation. Number 7 is exposure time. Retention time, the duration for which materials are exposed to corrosive conditions, including acidic condensate, is a critical factor. Prolonged exposure increases the likelihood of significant corrosion damage. Number 8 is fluid flow and velocity. Flow conditions, the velocity of flue gas through pipes, ducts, and heat exchangers can influence heat transfer rates and cooling, impacting condensation rates and the distribution of corrosive agents. Stagnation areas, areas with low fluid velocity or stagnant conditions can lead to localized corrosion. Number 9 is environmental conditions. Ambient temperature and conditions, external environmental factors, such as temperature and humidity in the surrounding area, can also influence the internal conditions of flue gas systems, affecting dew point and condensation. Number 10 is regular maintenance and inspection. Monitoring and maintenance programs, regular inspections, maintenance, and monitoring of materials can help identify early signs of corrosion and allow for timely interventions to mitigate damage. In conclusion, understanding the critical factors of flue gas dew point corrosion is essential for designing effective mitigation strategies and maintaining the integrity and performance of industrial systems. By addressing these factors, especially temperature management, material selection, and operational practices, facilities can significantly reduce the risk and impact of corrosion-related damage. Regular maintenance and monitoring are also crucial to identifying and managing potential issues effectively. Flue-Gas dew-point corrosion affected units or equipment based on API 571R, Number A. All fired process heaters and boilers that burn fuels containing sulfur have the potential for sulfuric acid dew-point corrosion in the economizer sections and in the stacks. Number B. Heat recovery steam generators, HRSGs, that have 300 series SS feedwater heaters may suffer chloride-induced stress corrosion cracking from the gas side, OD, when the temperature of the inlet water is below the dew point of hydrochloric acid. Number C. 300 series SS feedwater heaters in HRSGs are potentially at risk if the atmosphere of the combustion turbine includes chlorine. Cooling tower drift from cooling towers that use chlorine-based biocides may blow into the combustion turbine and lead to potential damage in the feedwater heaters. Flue-gas dew-point corrosion can affect various units and equipment in industrial settings, particularly those involved in combustion processes, power generation, and waste management. Below are some of the key equipment and units vulnerable to this type of corrosion. Number 1 is boilers. Boilers impact. Boilers are at risk due to the presence of flue gases, which can condense and lead to corrosive environments, particularly in superheaters, economizers, and ash handling systems. Number 2 is heat exchangers. Heat exchangers types. This includes economizers, air preheaters, and other heat recovery systems. Heat exchangers impact. Contact with flue gases can lead to condensation, resulting in corrosion of tubing and shell materials, particularly if they are not designed for acidic environments. Number 3 is chimneys and stacks. Chimneys and stacks impact. The inner surfaces of chimneys and flue stacks can be severely affected by acidic condensates that form when flue gases cool rapidly. Corrosion can lead to structural damage and reduced lifespan. Number 4 is ductwork. Ductwork impact. Ducts that carry flue gases from the combustion process to exhaust stacks or heat recovery systems can suffer from corrosion due to condensation of acidic vapors. Number 5 is burner and combustion systems. Burner and combustion systems impact. Burners that operate under conditions leading to low flue gas temperatures may experience corrosion, particularly if combustion conditions lead to higher levels of sulfur or chlorine compounds. Number 6 is condensate drains and collection systems. Condensate drains and collection systems impact. Systems designed to handle condensate may corrode due to high acidity, especially if proper materials are not selected for drains, traps, and other components in contact with water and acids. Number 7 is ash handling equipment. Ash handling equipment impact. The corrosive nature of the ash when mixed with acidic condensates can lead to corrosion in ash transportation and handling systems. Number 8 is piping systems. Piping systems impact. Pipes that transport flue gases, especially in areas where temperatures drop below the dew point, are at high risk for corrosion due to condensate formation. Number 9 is refractory materials. Refractory materials impact. Refractory linings in furnaces, kilns, and incinerators can suffer damage from acidic condensates, leading to degradation and reduced lifespan. Number 10 is fans and blowers. Fans and blowers impact. Fans used for flue gas recirculation or exhaust may experience corrosion, particularly if they are made of materials that cannot withstand acidic conditions. Number 11 is gaskets and seals. Gaskets and seals impact. Non-metallic seals and gaskets in flue gas systems may deteriorate due to exposure to corrosive condensates, leading to leaks and failures in the system. Number 12 is storage tanks and silos. Storage tanks and silos impact. Any storage units that may be exposed to acidic condensate, such as those used for chemicals or materials affected by flue gas exposure, can be at risk of corrosion. In conclusion, flue gas dew-point corrosion poses significant risks to various units and equipment in industrial settings. Understanding which components are vulnerable can help organizations implement appropriate design considerations, material selection, and maintenance strategies to mitigate corrosion and ensure the safe and efficient operation of their systems. Regular inspections and monitoring of these units are essential to identify and address potential corrosion issues before they lead to significant damage or failures. Flue gas dew-point corrosion appearance or morphology of damage based on API 571, Number A, sulfuric acid corrosion on economizers or other carbon steel or low alloy steel components will have general wastage, often with broad, shallow pits, depending on the way the sulfuric acid condenses. Number B, for the 300 series SS feedwater heaters and HRSGs, stress corrosion cracking will have surface breaking cracks and the general appearance will be somewhat crazed. The appearance or morphology of flue-gas dew point corrosion damage can vary based on several factors, including the specific materials affected, the chemical composition of the condensed fluids, and the operating conditions. Here are some common characteristics and forms of corrosion that can be observed. Number 1 is pitting corrosion. Pitting corrosion description: this form of corrosion appears as small, localized pits or holes on the metal surface. Pitting can occur due to the presence of aggressive acidic condensates, particularly from sulfuric acid. Pitting corrosion appearance: the pits may appear as small, shallow depressions or deep holes that can penetrate the material significantly. Number 2 is general corrosion. General corrosion description: general corrosion will result in a uniform loss of material across a surface, making it thinner over time. General corrosion appearance: the surface may look dull or rough, and there can be visible signs of erosion. This can lead to a decrease in the material's overall integrity. Number 3 is galvanic corrosion. Galvanic corrosion description: if dissimilar metals are in contact within a corrosive environment, galvanic corrosion can occur, leading to the accelerated deterioration of the less noble metal. Galvanic corrosion appearance: this damage may manifest as localized corrosion, often leading to flaking or separation of layers, particularly around joints and connections. Number 4 is rust formation. Rust formation description: corrosion related to moisture can cause extensive rusting, especially on carbon steel surfaces. Rust formation appearance: the surface will exhibit reddish-brown rust scales, which may flake off and expose fresh metal underneath, leading to further corrosion. Number 5 is corrosive cracking or stress corrosion cracking, or SCC. Corrosive cracking or stress corrosion cracking description: these forms of corrosion occur when environmental conditions, e.g., acidic condensate, interact with tensile stresses in the metal. Corrosive cracking or stress corrosion cracking appearance: cracks that can appear as fine lines on the surface, which may sometimes have corrosion products in or around them. These can propagate over time and lead to sudden failures. Number 6 is erosion corrosion. Erosion corrosion description: a combination of mechanical wear and corrosion, often seen in high-velocity areas. Erosion corrosion appearance: the surfaces will appear roughened or abraded, with uneven wear patterns, leading to accelerated degradation. Number 7 is black or dark staining. Black or dark staining description: accumulation of corrosive products, including soot or created by condensation, may lead to visible dark discoloration of surfaces. Black or dark staining appearance: surfaces may become stained with dark deposits, often indicating the presence of sulfur compounds or other corrosive agents. Number 8 is acidic white rust. Acidic white rust description: certain high-temperature environments can produce whitish corrosion products, particularly from zinc-coated materials. Acidic white rust appearance: this may manifest as white powdery deposits, often indicating an attack on zinc coatings. Number 9 is scale formation. Scale formation description: in certain cases, deposits of corrosion products or other contaminants may form on metal surfaces. Scale formation appearance: scale may appear as hard, adherent crusts or flaky materials on the surface, reducing thermal efficiency and promoting localized corrosion. In conclusion, the morphology of flue-gas dew point corrosion damage is diverse and can manifest in various ways depending on factors like material, environment, and operating conditions. Regular inspection and monitoring are vital to identify these signs early and employ necessary maintenance or intervention strategies to mitigate further corrosion damage. Understanding the appearance of corrosion will help in assessing the integrity of equipment and planning for repairs or replacements effectively. Flue-gas dew point corrosion damage prevention and mitigation based on API 571, Number A. Maintain the metallic surfaces at the back end of the boilers and fired heaters above the temperature of sulfuric acid dew point corrosion. Number B. For HRSGs, avoid the use of 300 series SS in the feedwater heaters if the environment is likely to contain chlorides. Number C. Similar damage occurs in oil-fired boilers when the units are water-washed to remove ash if the final rinse does not neutralize the acid salts. Sodium carbonate should be added to the final rinse as a basic solution to neutralize the acidic ash constituents. Here are several strategies and best practices for preventing this type of corrosion. Number 1 is material selection. Use corrosion-resistant alloys, selecting materials that have better resistance to corrosion, such as stainless steels, e.g., 316, 310, or nickel-based alloys, can reduce the risk. Coatings. Applying protective coatings, such as ceramic, inorganic, or organic coatings, can help protect surfaces from corrosive condensates and extend equipment life. Number 2 is design considerations. Minimize heat loss. Designing systems to maintain higher flue gas temperatures can help avoid conditions where condensation occurs. Insulating ducts and stacks can reduce heat loss. Proper drainage. Ensuring appropriate drainage in areas where condensation may occur is crucial to avoid the accumulation of corrosive liquids. Avoid low-temperature areas. Design ductwork and systems to minimize low-temperature zones where flue gases can cool and condense. Number 3 of the strategies and best practices for preventing this type of corrosion is operational practices. Optimize combustion. Maintaining optimal combustion conditions can minimize the formation of corrosive compounds in flue gases. This includes achieving ideal air-to-fuel ratios and controlling excess oxygen levels. Temperature management. Operating at higher temperatures can help prevent the formation of condensates, keeping the flue gases above the dew point. Number 4 of the strategies and best practices for preventing this type of corrosion is regular maintenance and inspections. Routine inspections. Conduct regular inspections of susceptible components to identify early signs of corrosion. This includes checking for pitting, rust, and other deterioration. Cleaning programs. Implement cleaning schedules to remove soot and corrosion products that can lead to further damage or promote additional corrosion. Number 5 of the several strategies and best practices for preventing this type of corrosion is monitoring and control systems. Condensate management. Install monitoring systems to check for the presence of condensate and manage pH levels of the fluids. This can include the use of neutralization systems for acidic condensates. Temperature sensors. Using temperature sensors and control systems to maintain flue gas temperatures can help prevent condensation. Number 6 of the several strategies and best practices for preventing this type of corrosion is chemical treatments. Corrosion inhibitors. Using chemical inhibitors in the system can help protect areas exposed to corrosive condensate, although comprehensive system compatibility should be evaluated. pH control. If acidic conditions are prevalent, using neutralizing agents can help maintain a pH that is less corrosive to susceptible materials. Number 7 of the several strategies and best practices for preventing this type of corrosion is flue gas desulfurization, or FGD, systems. Installation of FGD. Implementing FGD systems can help to reduce sulfur compounds in flue gases, thus reducing the potential for acid formation and subsequent corrosion. Number 8 is insulation and heat recovery. Insulating surfaces, heating surfaces, such as ductwork and stacks, can help maintain temperature above the dew point and prevent condensation. Heat recovery systems. Utilize heat recovery systems effectively to capture waste heat and improve overall efficiency while keeping flue gas temperatures elevated. In conclusion, prevention and mitigation of flue gas dew point corrosion involve a combination of material selection, design strategies, operational practices, regular maintenance, and monitoring. By addressing these areas proactively, industries can reduce the risk of corrosion-related damage, enhance equipment longevity, and improve overall operational efficiency. Regular assessments and updates to corrosion management strategies are essential to adapt to changing operational conditions and chemical environments. Flue gas dew point corrosion inspection and monitoring based on API 571, Number A. wall thickness measurements by UT methods will monitor the wastage in economizer tubes. Number B, stress corrosion cracking of 300 series SS can be found using VT and PT inspection. Inspection and monitoring are critical components in detecting and managing flue-gas dew-point corrosion damage. Various methods can be employed to identify early signs of corrosion and evaluate the health of equipment. Here are some commonly used inspection and monitoring methods. Number 1 is visual inspection. Visual inspection description. Regular visual inspections are typically the first step in detecting corrosion. Inspectors look for signs of corrosion, such as rust, pits, cracks, and discoloration. Visual inspection tools used, binoculars, borescopes, or cameras may be used to inspect hard-to-reach areas. Visual inspection frequency. Inspections should be scheduled regularly based on the likelihood of corrosion and operational conditions. Number 2 is ultrasonic testing, or UT. Ultrasonic testing description. Ultrasound waves are used to measure the thickness of metal components. A decrease in thickness can indicate corrosion. Ultrasonic testing advantages. This method is non-destructive and can provide accurate measurements of wall thickness, helping to identify areas at risk of failure. Number 3 is radiographic testing, or RT. Radiographic testing description. X-rays or gamma rays are used to create images of the internal structure of materials. This can reveal internal corrosion and structural integrity. Radiographic testing advantages. RT provides a permanent record of the condition and can detect hidden defects not visible through other inspection methods. Number 4 is electrochemical testing. Electrochemical testing description. Methods like linear polarization resistance, LPR, and electrochemical impedance spectroscopy, EIS, can assess corrosion rates and mechanisms. Electrochemical testing advantages. This approach provides detailed insights into the electrochemical processes at work, allowing for better predictions of corrosion behavior. Number 5 is magnetic particle testing, or MT. Magnetic particle testing description. This method involves applying magnetic fields to detect surface and near-surface discontinuities in ferromagnetic materials. Magnetic particle testing advantages. Highly effective in detecting weld defects and surface cracks that could compromise corrosion resistance. Number 6 is dye penetrant testing, or PT. Dye penetrant testing description. A dye is applied to the surface of a material and allowed to seep into cracks. After a specified time, excess dye is removed, and a developer is applied to bring out the cracks. Dye penetrant testing advantages. Particularly useful for detecting surface cracks and porous areas that may lead to localized corrosion. Number 7 is thickness gauge measurements. Thickness gauge measurements description. Portable electronic thickness gauges measure the residual wall thickness of pipes or structures, identifying areas where corrosion has occurred. Thickness gauge measurements advantages. Provides quick thickness measurements and can be used in the field. Number 8 is thermal imaging. Thermal imaging description. Infrared thermography can be used to detect temperature variations on surfaces, which may indicate areas where corrosion is leading to insulation failures or heat losses. Thermal imaging advantages. A non-contact method that can help identify issues before they become critical. Number 9 is condensate monitoring. Condensate monitoring description. Regularly sampling and analyzing flue-gas condensate can provide insights into its chemical composition, including pH and corrosive species, like sulfuric acid. Condensate monitoring advantages. Helps in understanding the corrosive potential of the condensate and can guide mitigation strategies. Number 10 is predictive monitoring systems. Predictive monitoring systems description. Utilizing sensors and data analytics, predictive monitoring can assess operating conditions and equipment performance in real time, identifying potential issues before they lead to significant damage. Predictive monitoring systems advantages. This proactive approach allows operators to make data-driven decisions regarding maintenance and operational adjustments. Number 11 is corrosion coupons. Corrosion coupons description. Inserting corrosion coupons, metal samples, into the system can help assess the rate of corrosion in real conditions. Corrosion coupons advantages, allows for a comparison to industry standards and provides actual data for determining material degradation over time. In conclusion, regular inspection and monitoring are essential to detect flue gas dew point corrosion damage early and efficiently manage the integrity of equipment. The choice of method often depends on the specific circumstances, including material type, operational conditions, and accessibility of the components being inspected. A combination of these techniques can provide a comprehensive understanding of the corrosion landscape in flue gas systems, allowing for timely interventions and optimized maintenance strategies. Thank you.